we know that a power series can be differentiated. So for example, this is a power series, and this is the function. They can be differentiated, and they will be equal to the new power series is equal to the derivative of the function. So if I differentiate this, sorry about that. If I differentiate this, I will get this. But if I differentiate this, I will get so this is actually the power series for this function. Now, something a little strange here. This thing here is n minus 1. It starts from n equal to 0. But if you write it out, it's actually n starting from 1, because you see, this is actually 0 times x to the minus 1 plus 1 times x to the 0, which is just 1, plus 2 times x, so on and so forth. So really, this is actually just starting from n equals to 1, because this thing is not there. So that's just an explanation why we change n equals to 0 to n equals to 1, because n equals to 0 is not really doing anything. So let me rewrite this. Sorry. This has to be changed, and so it's not 0 anymore, but it should be a 1. So this is where we get, this is where we're at. If we try to differentiate again, we are not going to get n times n plus 1, because if we try to differentiate this again, and differentiate this again, you will get n times n minus 1. This is not what we want. This is not what we want. Right? We want an n plus 1. So this is not good if we differentiate. Not good. So what should we do? We should multiply by x squared first. And if we do that, our series will become n x to the n minus 1 times x squared. But because x squared goes inside, it can be rewritten as x squared here. And if you simplify, x to the n minus 1, x squared, these two together gives you x to the n plus 1. Now, if I differentiate, I'm very sure I get n times n plus 1. So go ahead. If I differentiate on the right side, I will get n times n plus 1 x to the n. And the left side, well, I'll leave it to you. You differentiate and get a function here. So this is how you approach the problem number 6.